But he should be here for our meeting. It's one of our most important. I have some doubt whether how can we make this what's the representation open for discussion. Yes. Okay, it's almost time to start. It's time. Okay. It's time. Yeah. Hello, guys. It's 3:40, so it's time to start our meeting. This is the proposed network machine learning research group. So if you are running, if you happen to be around room, you still have a chance to find your right room and get the right meeting you want. Before we start, I would like to summarize a little bit for the what happened last year. This is actually our fourth meeting. We have our first meeting last November, and we also have the successful meeting in Buenos Aires. And 3 weeks ago, we had our number 3 meeting in Athens. We discussed the many use cases already. This is our fourth meeting according to regulation of IETF. So we almost reached the end of the period for 1 year primary time. So if we create stable community, research community for this topic, then we probably have a very good chance to transform to a formal research group, maybe before next meeting, hopefully. Today we have 2 hours for our meeting. First thing, we still have the IETF IPR policy. If you would like to publish anything or to presentation here, you need to follow this policy. Before the meeting, we have the mailing list for the LRG, and we have the web page, also the wiki page to keep track. This RG is chaired by me, Xinjiang, and my co-chair, Albert Carbonos. Blue sheet is already passed on. Please make sure you sign the blue sheets. We need at least a minute taker. Any volunteer for that? Volunteer for minute taker? Bing, could you take it? Thank you. We have the remote participation support. We actually have 1 remote presentation today from Grace. All the slides already uploaded in the material web page of this meeting. It will also show on the proceeding of our research group. This is the meeting agenda. For this meeting, we actually have much more open discussion rather than before. For most of our previous meeting, we are full of presentations, which most discussing the use cases. But this meeting, we think we reach a crucial time. We do understand a few use cases we already started, and now it's time to discuss, what may be the next step. We still have the first hour for the use cases, including the security monitoring in the internet, the use case of phishing by Jeremy, and apply machine learning mechanism with network traffic by Bing Liu. Mobile network state characterization and protection made by Viola remotely from Grace. The last one, I just get informed the other cannot make it. Then for the second hour of today's meeting, we have two open discussion. One is on the potential standards dataset. We all know dataset is very important for the machine learning, but whether it's possible to make it standards, I'm not sure. So that's open for discussion. And there are a few questions or potential direction we could have for this research group. That's also subject for discussing. Any agenda passing? Once, twice, gone. Okay. So next, Jeremy. Go ahead.
Thank you. So, what's wrong? Yes?
It's on.
Okay, so my talk is about security monitoring in internet. So,
get closer. Yeah, it's on,
okay.
But closer.
Okay, so I will present mainly one use case we have investigated, which is a use case of phishing. So next slide, please. Yes, that's fine. And so the first part of my talk just rapidly describe how we basically do some kind of monitoring of the internet for our security research. So basically, as usual, we want to collect some traces or logs of attacks and kind of malicious activities. So what we have developed just a platform where we can host some honeypots. And as you can see on this picture, his idea was that we have this platform, which is great because we, in order to not appear as a research institute, we are able to subscribe some, let's say, residential customer as residential customer to ADSL and so on. So we appear totally as a normal user of internet. Next slide. So here is currently the types of honeypot we are running. So we have different ones. Some are really dedicated to web vulnerabilities, other for example, for industrial system as well. We have some which are more like oriented toward ACCH or for more like shell connection attempts. So we have connectivity over internet that people can reach us, so they can discover we have vulnerabilities, because if you want to collect attacks, of course, you have to expose some vulnerabilities, that we have done. And also we are monitoring more standard stuff, like we have NetFlow, we are collecting NetFlow, syslog, and so on over all the system. Next slide, please. Here are just some numbers. So regarding what we have collected from general point of view, I mean, it's not specific to one type of attack, but you can see the total number of attacks we have collected. until basically 2 years ago. So why we stopped 2 years ago? Because last year we completely, let's say, reshaped the system. We did some tests, and now is again in production with a new version of a lot of software and so on. So it's a very nice platform. You can collect a lot of attacks and so on. And next slide, please. Yeah, just some type of information you can rapidly get from this type of platform. We can, for example, know what are the type of passwords which are attempted on our honeypot shells. Next slide. So, yeah. So, what was the last evolution? Is the problem? Okay, we have a lot of honeypots, so we can collect attack, but most of the time we are collecting either the same type of attack or we are not very attractive. So, the idea was to be more proactive, meaning just rather than just waiting the attack, going where basically you have some malicious content. For example, where you have some binary to download, where you may have some website which will try to get you downloading some file and so on. So that's what the idea is. So there are honeypot as well that do that. For example, we are using tag currently, which you provide the honeypot a list of a URL to go, and then it will start to check the web page from content to download. And then we also went with this use case of phishing, because you have a lot of tools that can that exist that will check if a web page may be used for phishing or not. So it depends on various techniques. So the simple one, of course, is blacklist. But blacklist it supposes that, of course, you know that the website has been tagged as containing some kind of phishing, which is not most of the time not done in time regarding the lifetime of phishing technique. If you look at the study, most of the phishing campaign are very powerful in the first 24 hours, and most of the time blacklist has not yet updated at this time. So the idea was to have mechanisms that will help, or honeypots that will just go to these URLs, because you have then tools that can check the content of the web page, the kind of, how to say, even some visual inspection of the web page to see if it looks like some other normal institutional web page. So you have tools that do that, but of course you know where to look for. And it's what our idea here is, try to either predict what will be URL which will be used for phishing, or what I will present today is if someone basically provides you a URL, because you can take all the URL you get, for example, in the email of your, I don't know, your user in your network, and you say, okay, there are probably phishing to that. It needs a lot of processing to check all the URL, and so we propose a method to rapidly select the one which are the most probable used for phishing. So next slide. So if you look at the characteristics of URLs, as you can see, there are a lot of words which compose URL, for example, which has nothing to do with the rest of URL. So for example, looking at the example here, so the first one is a phishing example towards PayPal, and you can see that, for example, here the rest of the URLs have nothing to do with the PayPal keyword, and so on. And it's the same for the user. It means that from a semantic perspective, if you look at normal URL and the one used for phishing, they are made from different type of words. At least, the thing we observed in phishing URL is that you have usually the brand, the company which is targeted by phishing. We have some keyword related to this company, and a lot of stuff which has nothing to do with it. So we start from this, and yeah, if you can just, yes, maybe just go back one slide. I think it's maybe the color does not really appear well, but so what we will use basically is we decompose here the URL in different components, and yep, in particular we'll just extract this, the main level domain and the public suffix, and we'll take also the rest. Next slide, please. So yes, this is the main assumption, is that if you are normal URL, being in URL, normally all the words or all the terms that compose it should be related, which is not the case for phishing. So this is the main assumption, and on some point we think that the word using URL are really similar to the keywords that you can use. For example, you type a query in a search engine. And so we build a kind of internet vocabulary which helps us to analyze what is phishing or not regarding the URL composition. Okay, next slide, please. So yes, so as I said, now we take the different part here, which is the main level domain and main level prefix, which compose this part, and then the remaining URL. We take all the terms, meaning that we do some split regarding the code, the number, and so on. And we take these two sets of elements. This basically composes our terms, and then we will compute metrics over these terms. Next slide. So all we do, we will rely on kind of semantic analysis, relying itself on what we call the internet vocabulary. But of course, what is it basically? We took statistics from Google and Yahoo over queries. So basically, we took two types of statistics, which are not exactly defined as the same for both search engines. But one is terms which are related, meaning terms which are queried, how to say, queried just one after other. So you make first query and then the second query, and there are two queries, but terms of both queries will be related, and the associated term will be that terms will appear in the same query. So starting from that and the two previous sets, we now compose for each of these sets two new sets, which are the associated terms and the related terms. Next slide. And so based on that, we compute a lot of metrics because we don't want to be, we want to be exhaustive at the beginning. And so what we compute simply, we will just compute cardinality over the initial set of words. Then we'll compute also cardinality over the new set of words. And we continue, for example, here we just simply use Jacquard index between the different sets to see if, of course, just to measure a kind of similarity between the set, assuming, of course, you take two URLs at the beginning, you extract the different set, and you will compute all this similarity. We have also some popularity, but that's fine, that we use from, for example, from Alexa top ranks that you can use to extend also the feature set. Next slide, yes, please. So yes, and what we do is that, of course, we have a lot of features, and then it's the time to apply some kind of machine learning. So we just apply a different one to test a bit. So we build a data set from both legitimate and phishing URLs, of course. And then, yes, we test different classifiers, and here you have the result with the different classifiers. Looking at that, we saw that the random forests were the best. Of course, we did some kind of parameters adjusting. We should maybe have done more, but okay, look like we already have good results with an accuracy around 0.95. But which does not really appear there is, of course, the false positive, which is a bit here at the LG right, 1.44. So okay, look like we are able with this method, taking an URL, we are able to classify, of course, after learning over other URL, to classify as a phishing URL or not. But if you go a bit further, if you go next slide, which is more interesting, since we use a random forest, you can use as a result as a strong result. It's what we had before. We are still able to have this result in less than 1 second, so it's very rapidly to say that this URL is phishing or not, with of course some false results. But if now you look at the soft score, because I mean you have a random forest, so you have different decision tree, and each decision tree votes if it's phishing or not. And you look at this as a proportion of trees that vote for one decision of another. And you look at more, if you look here, for instance, it depends. Here, basically, it's when you have a majority. of trees, the majority of trees is voting basically that are legitimate. And of course, this represents a false positive, okay? And you have the same here, they vote, but for this case, the majority vote for phishing. Of course, you have also some false negative. So rather than just taking the result as directly, what we propose in this work then is to say that, okay, if you just consider the result where you have a high confidence, meaning is on the extreme limit of this graph, then you can read the result. For example, you can be very close to 100%, even if you know we will never reach it. But of course, only on a subpart of the dataset. But anyway, we are higher than 99% with for more than 80% of the dataset. What it means, and you can go then to the conclusion. What it means is that we don't believe that we can be fully discriminative using just a classifier. We don't believe that, but we can really guide the analysis, because if you remember the problem that you have at the beginning is that if you provide a lot of URL and you have to check, I mean, you have, meaning just taking back in the context, you have the honeypot that will connect to the real, which is the contents, then some algorithm, because you have to test different methods, then to verify if it's phishing or not. It can be very long. So what we propose, rather than checking every URL, we will only check the one which either we are sure they are phishing. So this is the extreme at the right of the previous graph, or the other one which are the middle, which we are not sure. But for the other one for which we are almost sure that they are normal URL, we can really rapidly discard them. And so reduce, basically looking at the graph before, it was like you can exclude 80% of the data set, like that. And based on that, of course, then you just concentrate your analysis, which is more costly, because methods to really verify if it's phishing or not are more costly, only on those specific URL. So yeah, that's fine. You have some reference. This work is basically has been done in cooperation with the University of Luxembourg as well. In particular, it was under the thesis of Samuel Marshall. So that's it for me. And if you have any question, I will be glad to answer.
Dave Meyer, two kind of quick questions. One, what are the assumptions underlying your model? So for example, are you assuming that the components of the URL are interchangeable, like, you know, it's a bag of words style or something else? And the second one is, did you consider using any kind of statistical clustering technique on categorical data like LSI or LDA or any of those kind of things?
So the so to answer the first question, yeah, so main assumption of this work is that words that compose the phishing URL are not all related. I'm kind of, okay, at least we have not the same relation from a semantic point of view when we look at normal and phishing URLs. That's the kind of first assumption we have. Then, before that, we don't really look at the sequence of words. We just look at what, for example, usually when you have just imagine you have PayPal, Microsoft, and so on, what usually the rest of the URL is composed. And then we look on phishing URL, what is composed of phishing URL. Usually you have a brand you target, or a company you target, and a lot of stuff which are not very related. Because something classical, you register a domain which has nothing to do with what you target, and then you have some keywords that you add just to make the people confident that it's normal related URL. So that's the first thing. So yeah, and for the second question, then we did not. We did not test our method against all existing techniques, particularly from statistical-based techniques. What is the core here of the technique again? And for me, in machine learning in general, is that we are really engineered on the feature set we use, and this will give you really the value. Then we have, of course, some metrics, and yeah, this can be also used for other techniques as well. I mean, you have two parts. You have the feature part, that feature and metrics, and then you have the algorithm part. And okay, the algorithm part can be changed for sure, but I cannot give exactly the result with any algorithm that you can test.
Yeah, great work, Jerome. So just trying to understand, as a ground truth, you're using fish tank or strain. So you collect your features and analyze URLs from fish tank. That's how you run it, right? Yeah. That's just a couple of statistics. Oh yeah, I'm Giovanni. I work for SIDN and DataNL TLD, so we have a big interest in phishing too. 90% of the phishing we've seen are from URLs like what you just shown, because these phishers, they typically hack into CMSs or content management systems, and it's cheaper for them than perform like register a new domain and put it up online. But doesn't mean that their URLs that it's just one top level domain, they're less dangerous than the ones with a long URL. So I think I'm trying to say here, your work is really good. I mean, we should talk offline to talk, maybe to collaborate some things together. Because we have different data sets, like, queries for authoritative, we have like registration data, so maybe you can combine with that and use it as features. Okay.
Yes, thank you. Yes, so yeah, we have also looked, I didn't present here, on the domain part, where we are even able to predict in advance what will be the kind of next registered domain for phishing. And so we have some work on that, so we can discuss on that. But of course, then at least if you combine with DNS, DNS features from registration, then you can really should be able to have more insight of what is used the URL or the domain for.
Hi, Jerome. Vijay Kurbani from Bell Labs. I'm aware of this work based on Mark Samuel, apparently. Can you go back a couple slides? Yeah, one more, please. Okay. So 94.91% accuracy is on all of the data set. Yep. But 99% accuracy you're saying is on 80% of the data set. Is that?
Yeah.
Okay, I thought you were getting 99% accuracy by maybe combining some of the classifiers, but that's not the case here.
No, we got 99 just by taking the value which are more confident for the result of the classification. Meaning that the idea for this URL, you don't need extra validation check. You can just say, can be very well confident in the result. For the other, you need an extra mechanism that will, for example, will connect to the website, will do something which I like is visual similarities with other websites to see if it looks like another website.
Did you entertain the idea of using maybe one or two more classifiers and using a combination function of sort to distill the results? Sort of what we did with Samuel in the SIP space.
Yeah, there are of course some space for improvement and room for improvement to is using other type of combining classifier. So it's we have not yet investigated this, but this is something. So for us the next step really is to use this purely research work, which we integrate into the honeypot part in order to automatically connect into the internet to the different URL. So this is the first next step, having all the system in place, and then we will maybe improve let's say the backend that will generate the URL, because we have the URL here, and then you want to.
I think it might be interesting to maybe take a look at C5.0 and JRIP and see if you can combine them in any way. And one last question. I was surprised at the results of SVM. They seem to be almost towards the low end. Is that just straight SVM, or did you tune it at all to run it?
I mean, so the thing we have done for this work is we push to the same as let's say the first parameters, and then we try to improve the one which looks more promising with parameters. For me, I think when we discuss, I think the most problem here that we have is that we didn't really engineer on as a kernel function. If you looked a bit more on that, because I worked a lot also with SVM before, and I know that if you're really able to tune the kernel function, that you can really have.
That would be my expectations as well. Thank you. Good work.
Hi, Xing here. I had two questions. First, do you have any autonomic follow-up, or is that possible to set up some autonomic follow-up, like autonomic filter based on the result?
You mean atomic?
I mean, you here your analysis is aiming to get the efficient URA, then you try to filter it or block it. So can you, based on the result, based on the accuracy, are you confident to do that automatically, or
No,
when the result improved?
Original idea of the work is what we have started to work is just to have kind of plugin over browsers that gives some advice to the user, but we cannot really block because I think it's you have the problem is with false positive, and so then the idea that we have is more using this. As I said, we took all the URL we can collect over our emails, and then select the one for the honeypots, because they will really connect to them and do more further verification. But of course, if you do that for a normal user online, I mean very online in real time, it may take some time. So in terms of latency, I don't see it can be really useful. But of course, when we have system production, the honeypot will do, and will then, of course, if it's confirmed that it's phishing, it will just populate a blacklist that we will, of course, distribute. So
you are saying this solution you have is going to help some human administrator to quickly take action based on your results, but still lead to human configuration. Is that right?
So I'm not sure to have well understood, but the idea is really that we can in real time, what we can do is just we can classify URL very rapidly. Mm-hmm. So I mean, if you think from our processing from the that you have in the lab, so we can take all the email from the lab that we got, just extract the URL. Based on that, we can check if they are phishing or not. Not real time from the classification, but not from the further checks. That's the problem. That's the long problem. That's a longer process. Mm. But then we can have either block directly or provide the blacklist. This can be, the session can be fully automated. So then it just depends. It's the time of the user to click to open the mail and click on the link. Okay. But as the admin, you can do that before. But depends, of course, if the user is always connecting and clicking on the link on the first opening. But of course, in a browser, it's more difficult because you have the last part of the session, which can be long.
Yeah. My second question is how much the solution is generic. When I say generic, is how if you change to another network, how much the solution you have to change to get really useful in the new network.
So so what we have validated here, of course, it's only based on one type of blacklist that we have. We already tested others. So yes, of course, there is probably a bias because usually blacklists are populated by people that seems to have received the phishing mails and checked, and then the blacklist is updated. It's what we take as an historical value, and so we can just validate over that. How generic it is, then the problem is also another study we did some trends, and because of course phishing campaigns are based on trends. You have the sales, then you have Christmas and so on. You have sport competitions, and so you have it's not only depend. You cannot build a global global data set. And we saw in previous study, we have related that every 3-4 months you have to retrain the system, which seems quite able during 3-4 months.
Yeah, I'm actually thinking whether it's possible, we set up some solution, like autonomical solution to pick up the future for the machine learning mechanism. Then, that means the whole solution could evolve by itself, to get the feedback from the time.
Yeah.
Yeah.
This is something which is we can reasonably say it's possible, because if you have this even longer last step at the end, we have a further value. We can request over the phishing URLs we have that we say that it's phishing. We can request longer verification, which we might be more confident. If you go on the URL, you don't know the malware and you don't know the binary and the signature is not to be a virus. You can easily say that yes, probably you have been redirected to a website which is not. Which contains some malicious offensive content. And so you can repopulate or do some kind of reinforcement learning on that as well. Yeah. But we didn't have yet that so far.
Okay, thanks, Jeremy.
Thank you.
So our next being
do I need to speed up because the
That's
last
fine.
discussion is
That's
taking too
fine.
much time?
oh, take your time.
Okay. Okay. Good afternoon, everyone. This is Bin Liu. The applying machine learning mechanism with network traffic. Next, please. So in last IETF, in Buenos Aires, the NMLRG meeting discussed several use cases of applying machine learning technologies into traffic handling. And there are some distinct and very interesting use cases from different organizations. And we had a lot of discussion. And after the meeting, we combined these use cases into one draft, which is shown as the slide. And apart from the use cases record, we also include some analysis and summarize of the methodology of how to apply and the motivation of applying machine learning to traffic area. So this presentation, I won't iterate the use cases again. It's mostly about the analysis and summarize part of the machine learning in network traffic area. So the motivation of why we focus on the network traffic, because as we know, you along with the internet services development, the user content is becoming more and more sophisticated, especially nowadays. There is more and more services based on the encryption transport. So it is becoming more and more challenge for administrators to get to know about the network status through exploring the traffic. And since the traffic has a large amount of information and it is flowing, always flowing on the internet, so it's very natural to think about using technologies such as machine learning to handle the sophisticated tasks. So that's a basic motivation. Next, please. So in this draft, we analyze the methodology into 4 aspects. The first one is the data of the network traffic. what kind of valuable information probably hiding in the network traffic. And then when a system is able to learn something, it needs some formalized data. So where's the source of the data and how they could be stored. And then there are some architecture considerations of the system. And the last one is the closed control loop. So based on the learned results, what actions could be autonomically act by the devices or the system. Okay, so for the first part, the data hiding in the network traffic. So we divided into several categories. The first one, we called it measurable properties, which means the latency, the packet count, and session duration, etc. These kind of information could be very essential for learning, and especially for the use cases relevant to quality of services. And the second category is the data within communication protocols. The protocol headers, there are a lot of useful information. The source, destination, IP, port number, and the application protocols. What is the specific protocol carried in the IP packets? There are various kinds of protocols. Next, please. And the type of the user content. So, for example, these users is browsing the web. Some others are accessing the emails and also the video, audio. This is also very useful information. And the last one is the data hiding in the signaling protocol. The signaling protocol means the traffic flows could be managed or manipulated by these signalings. The typical, it is about routing. Either it's IGP or BGP, and also some protocols like the MPLS traffic engineering and segment routing, which can influence the flow paths in the internet. And also some P2P protocols can influence the paths between users. Next, please. So for the data collection and storage, we can explore the data collection in two angles. One angle is from the forwarding devices. And for example, the devices like routers, switches, in theory, they could connect any data in the network traffic. But as we said in previous slides, for the measurable properties such as latency and packet count, this kind of information is very suitable for the forwarding devices to get and to record. And along with the forwarding devices, the terminals, which is the source or the destination nodes, they can also get some information, especially for the servers. They could provide some session statistics and the application protocols, the user content statistics, etc. And these devices, they can collect the data and save them into a central repository or they can also collect the data and storage by themselves for some local training. So some architecture consideration. The first one is the global learning versus local learning. So for the tasks that need a network-wide knowledge, there need to be multiple devices that do the, for example, the ensemble learning together to handle the common database. And for the local, one devices or a limited group of devices, they can directly learn the information collected by themselves. And for the case of grouped nodes, the data need to transfer between the nodes in the group. Next, please. The second consideration is the offline and online processing. So we call it a co-located mode, which means the training and the prediction is done within the same entity. And the training is, as we know, we also called it offline process, and the prediction we also called online process. And in comparison to the co-located mode, there's also a decoupled mode, which means the training could be done in a central repository. In this case, the central repository has a very large amount of data to be trained. But it doesn't mean the central repository need to do the prediction. The prediction could be done in other devices. And this training and the prediction procedure are separated. Next, please. The central learning and distributed learning. So the central learning means the whole process is done within a single entity. So mostly it is a central repository, such as the database and the network managed system, and also it could be a node, maybe a call router in a network, and distributed learning, which I just said. For example, we can use the ensemble learning among multiple devices. Next, please. Okay, the last one is, we call it a closed control loop. So when the system or node gets some result from the traffic data, and it can autonomically use these rules for the follow-up action. So this is called a closed loop. So either they can use the learned result to manipulate the traffic, for example, to change the flow path, or to change the next hop routing, and even changing some device configurations. There are various kind of parameters. And the closed control loop, because there's no human intervene, it must to get a very high accuracy. Unless we can guarantee the effect, it is very dangerous to let the system make decisions by themselves. So, so this kind of control might only apply to a small number of use cases. Okay. So It is now a 0.0 version document. So apart from the use cases discussed in last IETF, we also want some more contribution and reviews for these analyses and summaries of the methodology of applying the machine learning into network traffic. For example, do you find there's something very important missing in the draft? And the analysis for sure could be improved. And also the use cases description could also be improved. So we very appreciate your comment and your further contribution to this draft. Okay, any question, comment?
Doug Montgomery Nist. So do you have any ambitions for this draft to become something like gap analysis or another draft? I mean, it seems to be a couple of examples. Like, I was interested in things like doing an analysis of, you know, flow export technologies, NetFlow, IPFix, and the such, to see if they provide enough information for machine learning. I think the draft could have more value if it began to outline some things like requirements from other protocols to support machine learning and that sort of thing.
Okay, I think the bottom line is it is a informational document to show some result of current research or the industry utilization of the machine learning technologies in the network field. I think that's our bottom line, but I do agree it could be more valuable if there are some gaps or requirement indicators.
Maybe that would be a follow-on different draft.
Yeah, I guess so.
Yeah.
I mean, this draft is mainly based on, you know, what we already received from the last meeting, and that's still, you know, in very preliminary stage to just collect the examples and do some analysis based on those examples. What you suggest is definitely request more input. So until then, until we have those input, we may not be able to do such, you know, wide gap analysis. So
maybe it's suggesting a longer term goal for the research group.
Exactly. But that's definitely in the scope and in our mind for the research group to do such gap analysis in the future. Yeah. Yes.
Hi, Lars Eckert. So I just took a quick look at the draft, and I was surprised to see that the security considerations are very short, and they basically say there's really nothing for us to worry about here. And I wonder if that's a little bit inaccurate, right? Because on the top of my mind, right, you're talking about a system where data that potentially impacts user privacy is being shipped around, right? There's obviously some aspects here that we want to think about. And then we're going to throw a lot of compute at that data to learn stuff from it. Yeah. And that certainly has some security and privacy considerations, right? So I wonder if there's anything more that could be said here.
Sure, definitely. Points take.
Could we do that? Because
yeah,
so it seems very short-sighted to say there's nothing to worry about here, especially because machine learning, the entire point is to generate insights that you otherwise didn't have before.
Yeah,
and you can do a lot of good with that, right? But you can also derive other insights that are, de-anonymizing users even more than you can just do it based on the raw traces.
Yeah, actually, based on your comments, I believe we made a mistake there. We should leave it as TBD rather than just say
it's a 0-0 draft. Yeah, TBD would be way better than saying there's nothing to worry about.
Yes.
Got it.
You'll see that in the future version.
Hey, Dave Meyer again. Just following up on what Lars just said, I would encourage you to take a look at adversarial images or GANs, generative adversarial networks. You can actually poison the classifier if you build the right image, so you can do it here too. We don't understand exactly how this is happening, which makes it kind of worse, but you can, I encourage you to take a look at adversarial nets.
Okay.
That's the first thing. Second thing, can you go back to slide, the one that's called data of the network traffic 1-2? Back one more. So I would encourage us as a community and as a group to kind of understand the way that the language that's being used in the machine learning community for things like this. So what you're calling measurable here are actually generally called continuous or discrete, continuous and discrete. And the ones below that are generally called categorical because there's no Euclidean distance metric that makes sense to compare them with. So this is categorical. And so we might want to look at that and kind of get, kind of synchronize our information, our kind of terminology. I don't want to write a terminology document. Those are always terrible. But the next one is architectural considerations 3 of 3.
Sorry.
Okay, I'll figure out what I was going to say. Hang on, I got it. Sorry. Screensaver. Oh yeah. So is this the right one? This is the one that talked about ensemble learning. Yeah, ensemble learning usually refers to something different, and it could be applicable in sort of a centralized or distributed learning environment. It's kind of about averaging models, and so we might want to look at that as another axis to kind of think about this on. And then the last thing here is some models have limited accuracy, but I think it's a really bold statement to say that we're not going to get to accuracy like we're seeing now with speech recognition and things like that. I don't think we want to really say that because one, we don't know that, and two, it's sort of speculation, right?
Yeah.
Okay, thank you. I think both the terminology and the wording accuracy need to be improved. Thanks.
So, Albert Cabellos, can you go to slide 11? And I'm following up with Dave's comments. I don't agree that we shouldn't say that it has limited accuracy. I think that that's a very bold statement. And I don't necessarily agree with the section on closed control loop. I think that machine learning right now is being used for mission critical applications. And we don't know. In some cases, it can be as easy as identifying a flow. So identifying the application of a flow and then routing it based on whatever policy, which I don't think this will break any system, and it seems quite reasonable. Given that today there are systems to identify applications based on machine learning. And then following up on the first question, I think that maybe that it will be a good idea, maybe not for this graph, maybe for another one, to try to identify which are the traffic features that all the use cases are using, and try to see if there is any common ground, or maybe we can provide guidelines to other protocols and try to understand which are the most common ones or most useful ones.
Okay, for the first one, I basically agree that in current state of art, the machine learning mostly for assistant for humans decision, and it's not very reliable and even dangerous for the machine to make decision by themselves. But this section is providing some possibilities that maybe in some use cases, the accuracy is sufficient enough to do the autonomic.
We have self-driving cars, and I think that those are very mission-critical systems.
Yeah. But in any case, I guess we don't agree what you said here only for a small set of the use cases. We don't know that.
We don't know. That's
yeah. And the machine learning mechanism itself is developing in time. So we probably see better and better algorithm or mechanisms. Then that means we can apply machine learning to more and more solution use cases to be autonomic or closed control loop. Yeah.
Yeah, I think one potential area is that from our study experience, the network configuration sometimes is not a very accurate system. It just it can, for example, in routing we can configure the cost of the link, and it doesn't necessarily mean a very specific number. It just means maybe two different numbers distinguish with each other. So in some cases that doesn't need a very accurate configuration. Maybe the machine learning, even for the current algorithm, current technology, could be sufficient enough. But as we said, we don't know yet the use cases.
Lars, so the first slide that Dave asked you to bring up reminded me that another point that I forgot. Was it architectural considerations 1 and 2 or something like that? And what? Yeah, go back more.
No, that's
Go back more. Go back more. It was the one that was yeah, one more back. This one, right? So the things you list here, and I'm not a machine learning expert, so I don't know the terms I should be using, but a lot of them you have access to if the traffic is unencrypted. But we actually, for at least some networks, we're going to see a lot of encrypted traffic in the future, and it would be interesting to see. So if you fast forward and you lose access to some of these bits of information, what could you still do? Right, so maybe we have two kinds of networks, one where we have access to a much richer set of data where we can do a lot of things and maybe have pretty high accuracy, and then others, maybe those are more the consumer-facing networks where we have very little information or just a fraction of what's listed on the slide. And can we still do something interesting there?
Sure.
I think that's something that would be interesting to look at.
actually we in last meeting, ASENT, we had a presentation regarding to the encrypt data analysis. Did it? Yeah, that's bad.
Yeah, I wasn't in Buenos Aires, so sorry if I'm.
That's fine. Also, actually, second to your previous comments, besides the security section, we probably also need a privacy section. Yeah.
Thank you. Vijay Gravani again by Labs. Could you go to slide 10? I think not to hammer this anymore, but I think, as far as terminology is concerned, I've seen literature, for ensemble learning referring to multiple hypotheses in the same classifier. But here, I think what you're trying to say is maybe you have different classifiers and you have to somehow combine their results. But then if you do it in real time at a router, then your latency in getting the results from different routers or from different classifiers is going to have to be taken in account. Otherwise, you're just going to build up a queue, and that's not going to be very good.
Okay. The ensemble learning in these slides specifically means maybe not different classifier, maybe just one classifier, but the data set could be separated and learned by multiple.
Yeah, you sample different observations and use either the same hypotheses or different hypotheses on it. So, but anyway, I think the thing that you have to keep in mind here is if the ensemble is being done in the same router or versus in some parts of ensemble are being done somewhere else, and that's going to have an impact on how you process a decision for a packet.
Okay, thank you.
Hey, one more thing, and then I'll get out. Hey, I was thinking about what Albert just said, and it turns out that, and this is kind of, it's in the control loop piece of this. I think what's going to happen here is that in the very near future, we're going to learn that rather than, see, right now what there's an implied workflow here, and we haven't said what that is, but there's an implied workflow. It's something like this. Network thing generates a lot of data, you ingest that, you big data, you put it on the thing, you clean it up, and then you run some machine learning thing, and then there's an output from that, and you loop around inside that, right? And the output from that and what you decide on doing is essentially business logic that somebody wrote, right?
Yeah.
We want to be able to learn that. So the idea of control is really going to be much more general than what's being discussed here. And I would encourage everybody to kind of take a look at something like AlphaGo and look at how they learn what's called the policy network there. And that the policy network actually tells you how to behave. So it's the control network, right? And so I'd encourage us to kind of think about it a little bit more widely that way too.
Okay, thank you.
Okay. And we're done here. So next will be Verla from remotely. So
Yeah. I hope you can hear me.
yeah, I can hear you.
Okay.
Yes, clearly. So we need to next page. Just say so.
I have also activated the camera, but I'm not sure that you can see me. So
No, the quality is Rena, the quality is not good enough. Could you slow or try?
okay, I will disable the video because. Okay, so I'm Stavroula Vasaki from Wings and Intelligent, and I'm going to present you our work in collaboration with Professor Domesticas regarding the utilization of machine learning techniques in mobile network state characterization and prediction. As you can see, we will focus on two different problems of mobile networks. The second one has also been presented at the UCNC, so I'm going to be a little bit brief. The first considered problem refers to the surface classification in 5G networks. I should note that this work has been performed under the framework of a European Horizon 2020 project, Fantastic 5G. And as you know, a challenge. Next slide, please. Next slide, please. Thank you. Now, as you know, a challenge of existing as well as future 5G wireless communication networks is the satisfaction of diverse requirements from coming from heterogeneous services. More specifically, in 5G networks, we consider that we have diverse verticals, as you can see here, that will have different requirements, both in terms of quality of service as well as capacity. For example, mobile broadband services, mission-critical communications, vehicular planning, etc. So, a great challenge for 5G system management is to be able to identify its type of service and allocate the resources. Yes?
Rena, we cannot hear you very clearly.
Oh, do you want me to speak louder?
No. Could you try to be slow?
Okay. yes, of course. So, a great challenge of 5G system management is to be able to identify the services in order to be able to allocate it accordingly the network resources. A first step towards this direction, as we have said, is the identification of services. That's why we need an automated service classification mechanism. And in our approach, we have used the unsupervised machine learning techniques and more specifically classification approach in order to be able to identify in an accurate way the services and to have an optimal assignment of resources so as to satisfy the quality of service requirements of each service. Next slide, please. Now, obviously, each service, as you can see, has specific characteristics, both in terms of traffic as well as in terms of mobility. For example, as you can see here, MMC service is a periodic type of communication that refers to an exchange of small packets, whereas on the contrary, PMS, broadband multiband, refers to a non-periodic type of service with larger packets, exchange of larger packets. Furthermore, we can see that in case of MMC and MCC services, we are talking about low mobility services, whereas on the contrary, V2X refers to a high mobility service. So it's obvious that there are various service features that could be used in order to predict the service type in an accurate way, similar to the well-known traffic classification problem that you showed before. Next slide, please. So, in our initial scenario, we have considered three types of services: MCC, mission critical communication, massive machine type, and mobile broadband. And we have generated different types of MCC. Yes.
Rena?
Yes.
The quality is so bad. We cannot really hear you at all. So
really? I have stopped video. Do you want to speak slower?
okay. Could you we'll try to agenda the meeting. So we'll take the next agenda item. Then you may drop, then come back later to see whether that's improved. I don't think the current quality is any useful for the audience on site.
Okay, I will join again then. Correct?
Sorry, I have to cut off. Yeah. Okay. Yeah. I think. Okay. So next will be open discussing regarding the potential standard dataset. Yeah. Go ahead.
Okay, thanks. So if you can move to the next slide, please. Okay, so just to give you a little bit of context and some of the scope. So in the last meeting,
it's not a working group, and we're not standardizing it.
okay, yeah. Potential.
Potential.
Okay, not even potential.
It's the research group.
Okay.
Yeah.
So we discussed.
Actually, I believe what Albert will discuss is, whether we will be able to standard some data set which, is not standard in IETF standard.
So you can say that you will try to all agree to use a shared data set for experimentation, but if you use the word standard, especially if you say working group on the bottom of the slide, I'm reacting very negatively.
Sure.
So
Okay.
pick a different word.
Fully understand.
Okay, so yeah, it's the data set that's standard, not the. But point taken. So we discussed about data sets in this new area in network machine learning, and in this presentation, I would like to bring the attention to try to discuss with all of you to see if data sets are important or not. To try to discuss which is the importance of such data sets in other machine learning fields, and to trigger discussion about standard data sets, not the standardization of data sets. So next slide, please. So I've been reading quite a lot and trying to understand how important are data sets. And there are some people that argue that actually they are even more important than algorithms. And this is not precisely my point. What I'm trying to do is to bring attention to this issue. But it's not necessarily my point. So there are some researchers that argue that actually, if you take a look to the main progress that we have seen in artificial intelligence in the last years, it's more related to the availability of data sets than to the availability of algorithms. So here in this table, although it's not very clear, there are some examples. For instance, in the last row, if you take a look to Google DeepMind, which achieved human parity in playing some video games, this happened in 2015. And if you take a look, actually, the data set was available in 2013, and this particular artificial intelligence breakthrough is based on the Q-learning, which then they use deep learning too, which is an algorithm which is quite old. For instance, if you take a look also to IBM Watson, that became this TV show Jeopardy champion, this the data set which was based, this artificial intelligence algorithm, was based on a consolidated data set on many articles like Wikipedia and so on, which was available on 2010. But then the algorithm itself was designed in 91. And if you go back in time, you can also think about the Deep Blue, which beat Kasparov in playing chess. This was based on a data set of 70,000 chess games from 91, but the algorithm again is quite old than that. So again, I'm not trying to say that this is always the case or that data sets are more important than algorithms. My point is that Maybe they are less important than algorithms. It's very hard to argue that, or maybe I'm sure that there are many opinions, but if you go to next slide, but it is clear to me that at least data sets might be a limiting factor on the development of artificial intelligence techniques. So once we have the data set, then we can train the algorithm. It's not the other way around. That's at least what we have seen in the past. So if you go to next slide. So what will be the benefits of having public data sets in machine learning, in network machine learning? So, and the first item is something that it came up before, right? With the control loop and so on. So we are used we are very used in networking to have deterministic algorithms, that they work deterministically, and if you put an input, you know what the output will be. And those algorithms, typically, they provide you some guarantees. For instance, BGP is guaranteed to converge, and TCP is based on many deterministic algorithms, and we are used to have this kind of mindset. Well, the truth is that if we are shifting to machine learning, it is true that machine learning is not going to provide any kind of guarantee. And that's a big change. So then what do you do, right, in this kind of context? Well, typically what you can do is, if you have public data sets, you can actually test your algorithm that you have maybe trained in your network, but you can test it in a public data set and try to see if it is able to work in an unseen scenario, right? So you may have it won't offer any guarantees, but at least you can, if you have enough public data sets which have enough use cases, maybe you will trust a little bit more your algorithms. Then the second item is that it can be used to provide a benchmark. So let's say that we start developing algorithms. How do we know if one algorithm is better than the other one, which is basic, fundamental aspect in research, right? To do something which is best than the other thing. Well, typically in machine learning, they have data sets which are public, and then they benchmark how good they are against a well-known data set. Then, of course, public data sets will encourage research. I'm pretty certain about that. And another important thing is that it allows for reproducible research. So you can actually show why it works, on which cases it works, and so on. So if you go to the next slide. So here I'm trying to provide just some examples of public data sets that are available in other very well-known artificial intelligence fields. So for instance, if you go to computer vision, which is of course one of the largest one maybe, there is ImageNet, which hosts 14 million images for computer vision, and also it hosts a yearly challenge where researchers and groups around the world, they train algorithms, and then they go to this challenge to see which one is the best that recognizes more images or more objects, and so on. Also, for instance, quite recently, Yahoo News released a data set including 20 million anonymized users of news, and which users they prefer which kind of news, so that people can actually train machine learning systems to recommend actually news based on the anonymized data from the users. And if we think about it, in networking, actually, we are not that far away from this. Actually, there are many public data sets that are used for research and for many other things. For instance, and those are just examples, there are packet traces which are anonymized. For instance, Qaeda offers them, packet traces. Then we have RIPE Atlas, which offers a lot of measurements on latency, trace routes, pings, losses on the core of the internet. And there are, again, those are just some examples. There is Crowded, which is a huge data set on wireless networks, which includes many information from different networks, from different wireless networks, so that people go there, download it, and use it for research or to train algorithms and so on. So if you move to next slide, please. So that's the last one. So should we try to promote these public data sets? That's a question that I'm asking. I don't know if we should do that or not. And then there are already data sets in networking that are available. So do we need different kinds of data sets? So if we are trying to do network machine learning, do we need different data sets, or the ones that are available from networking are enough? Then something that also came up before, what are the privacy implications of such data set when used for machine learning? Are there many other associated risks, which I'm not listing here? And what are the most important aspects of these data sets? Maybe the features. Should we try to describe which are the most important features, or the way that we should benchmark the algorithms or anonymization techniques? So I'm very happy to see a queue. So.
Hi, I'm Brian Trammell. I've been working with network data with various degrees of openness for longer than I'd like to admit. The idea of having public data sets of network traffic is scary.
For now, second.
Yeah.
We are actually not only talking about network traffic.
Yeah, I know.
Yeah,
I know.
Previous.
Yeah. So there's BGP data, and there's a lot of BGP data out there, and there's the RIPE Atlas data. They're actually doing the right thing with respect to building a data set that you can actually use, and you just go get the stuff. And I mean, if you type nicely to them, they'll even let you bring a bunch of terabytes of disks by. And I think that this I'm going to edit your slide here and call that a research group, not a working group, because we're not a working group. I think that absolutely the research group, one of the valuable things this research group could do would be to have access to these data sets that already exist, and with a view toward using them for machine learning. Now, especially so, like a lot of this network data has been used for machine learning before it was called machine learning, right? Like reasons that a lot of this data existed was for doing an anomaly detection, which is just machine learning before it was cool. There's been a whole lot of work on privacy implications of data sets in this space. The IPFix working group published a informational RFC on anonymizing IPFix data, which is specific to flow data. Well, it was written about flow data, but it would be very useful for anything that's network traffic derived data. I think the standard thing is probably a gigantic rat hole. I think that, saying this is how you do network machine learning, because again, the point that you made in the presentation is very well taken. I'd go even farther than that. It's not just you need data sets in order to be able to train machine learning algorithms, you need good data sets. And one of the problems we've had in network research is it's very difficult to even be able to judge the goodness of a data set. Like one of the PhD students we had in our group did an anomaly detection thesis, but 90% of her time was spent generating synthetic anomaly data in order to train the thing, right? So, I mean, if you have an image data set that says dogs look like cats, then now your algorithm thinks that dogs look like cats, and this has been a huge problem in this space before. And the newness of the algorithms here, I don't think fixes that fundamental problem. So quality guidelines for these things with a view toward making them useful for network machine learning, I think would be a very useful thing that this research group could do. The privacy implications of data sets, the closer you get to traffic that actually represents traffic that's being generated by humans doing stuff with the internet, the scarier that is.
Just one interruption. Do you think that privacy also relates, because I agree, it's not only traffic. Maybe we want to release a data set, or someone wants to release a data set on the infrastructure.
Yeah.
So do you think that there are also privacy implications on
there
that?
are the way that we talk about privacy implications on the infrastructure is business confidentiality concerns, but it's basically the same thing. But I mean, like, even if you look at RIPE Atlas data, right? Like if I tell you what my RIPE Atlas probe is, and you do network machine learning on just the pings to the first half off my RIPE Atlas probe, you can tell when I'm downloading stuff. Because I've got a buffer on my router, and the buffering goes up, right? So I don't think it's possible to scrub any data set that's going to be useful completely. And if you look at some of your use cases are basically trying to reverse encryption, right? You have this effective encryption that's basically trying to take the payload and take it so people can't tell what's in the payload. And it's like, oh, but we want to see what's in the payload anyway, right? So, I mean, you have a fundamental, the types of stuff that you're trying to do in the use case that you're saying you want to do, you have a fundamental opposition to what these technologies are being. So, I mean, I guess these are all things that people know. I think that within sort of the smaller box where you're not talking about user data and you're not talking about classification problems, I think that it would be very useful. So this, talking about features that are useful versus not useful, sort of like guidelines for how to do research in this space, guidelines for what types of data sets are useful for using what types of algorithms to solve what types of problems. I think that in and of itself, like if you just made that the charter, the whole charter of the research group, or the whole statement of what the research group does, that would be very useful.
Yeah, good.
So cool, thanks.
Thank you.
Yeah. So when I first came up here, I thought, why are we standardizing these data sets? I mean, Yahoo releases their data set. Other companies, if you go to Kaggle, there's tons and tons and tons of data sets that you can use. Then it struck me that it's not the case that we want to standardize a vision data set or we want to standardize some other data set. I guess what we're trying to do here is specifically for network machine learning. So flows, for instance. But then raises the question that many of the public data sets you see, or many of the data sets that companies might want to release, typically will have just good data, right? And if you're going to be using any type of supervised learning techniques, then you need at least a reasonable amount of bad data, where you can figure out something is bad, as opposed to just using unsupervised techniques. So, and the other thing that struck me also is that moving away from flow data, you also need, if you look at many of the companies that operate large networks, you'll see that they maintain lots of KPIs, CPU usage, number of packets dropped, number of packets queued, all that type of information. Now, I haven't seen any public data set that has that type of information, because that you can use to correlate with flow data as well.
I fully agree. I'm not aware of any data set with such kind of information.
So I think, maybe the feedback then is to, if you're going to standardize something, then we need to scope it. And we also need to see if there's going to be some companies or somewhere where we can get different type of data sets, for attacks, so that you can use supervised learning, and for other stuff like KPIs, etc.
Good afternoon. My name is Elaine Newton. My background's in the area of biometrics, a very specific type of machine learning. And I can tell you from that you should also consider data sets that are sequestered, because when technology is less mature, public data sets are good for researchers, but as it matures, data or test sets run on public data sets can be tuned and gamed. So being able to have sequestered data is really where you want to end up, so you can have an independent test to really test capabilities. I was asked for a definition of sequestered data. I would say it's not public, except for maybe you might give people who are giving a product for testing, or a researcher giving an algorithm for testing, might be able to see some of the data in order to make sure that they can take in the data that they're given for a test, but most of the data would not be available to the.
Yeah, I understand that you are allowed to run your algorithm on the data, but you are not allowed to see the data.
Right.
Actually, one thing you mentioned is, the published data set is very useful for the unmatured technology, but so far we're still not sure how matured machine learning mechanism for networking or not. So maybe I'm thinking, we could some stage agree to try some published data first, then leave that to, if we can claim it's relevant matured, then leave that to the real data. Yeah.
Dave Meyer. A couple of things. First off, thank you for raising this, Albert. It's one of the things I've been on for a couple of years now.
Yeah.
It turns out that the incredible progress we've seen in machine learning more generally, not networking, but say in image recognition, speech, whatever, perceptual tasks, is really would not have happened without these data sets, MNIST, ImageNet, things like that. And if you look, you'll see that the pioneers in the field of, say, image recognition, what they did before they went off and did this work is they realized this was necessary. And I think we've gotten, it was necessary to have a data set that you could run your algorithm on and I could run mine, and I could objectively, mod gaming the system, say, hey, I've done better. my error rate's lower, basically, right? Or, whatever other components of that you were interested in. But I think we're a little bit confused. I think we got hung up on standard. What we really mean is we want open, so open didn't occur here. We want open data sets that are amenable to machine learning algorithms. So let's just use an example like ImageNet, like you said, Albert. ImageNet, you don't have to spend all your time cleaning the data because network data is ugly anyway, but image data was too, So you can pick up ImageNet and now you can run your machine learning algorithm on that without doing all that other work. So it allows you to work on the part of the problem you want to work on. That's number one. And then it allows you to compare, and it also allows you to build theories of how, for example, image recognition might work, like Jan Kuhn did and then you have, convolutional nets. And that's a theory of how image recognition works. We don't have anything like that for networking. Every single solution for networking I've seen is a one-off, every one of them, and there's thousands of them. So we don't have anything like that.
Yeah, that's something, I also consider that as the diversity of the task for in the network machine learning area, because we actually have many different, very different from each other, thousands tasks.
Whatever.
Yeah.
Right?
So I guess as kind of pioneer of we should first agree on some sort of maybe most important or maybe most durable targets. Then working on that first. Afterwards, we may get matured mechanism, or we may get some mechanism to be able to generalized.
Yeah. I'll just point out one other thing here. Well, something like MNIST or ImageNet or even some of the text databases that are out there seem like oh well, it's easier because images are just one hot encoded or whatever they are. In the early days of this, it wasn't. Everything was ad hoc, right? Mm-hmm. And so it's not really that different. It's just that we're starting way behind where this is, and so we got to kind of look at this and think about whether or not we can get to that. Because if you talk to any of the researchers in the field, one of the main things they'll tell you is that the progress they have had, this fantastic progress that's gone on over the last couple of years, is really because of the existence of these data sets, right? In part, anyway. So I think we need to get there.
Thanks.
Doug Montgomery. So I'd like to suggest that maybe jumping to data sets is one step too far, that you need to back up and think about, for specific use cases or technologies, how you want to test and benchmark it. Because as it was pointed out, you might download terabytes of network trace data, but if it doesn't contain the specific kind of events that you're interested in detecting, or them at several ranges of intensity, if that's the issue, the data set is useless. So I don't know how it would relate to a taxonomy of potential machine learning problems, but once you had in networking, but once you had such a taxonomy, then you want to talk about how you might want to go about testing and benchmarking these. And that'll give you some clue as to what kind of data sets you need. And some of them will have to be constructed, right? They'll have to be labeled. They'll have to be purposely constructed, because the terabyte network trace you download may not have the kinds of attacks or problems you want to address.
Yeah, I guess based on that understanding, probably one of the next step we could do is to agree on, in this research group, agree on a few use cases first, based on the existing databases, so which we can just access. Yeah.
Yes, Stephen Wright. Lots of good comments. I was trying to build on a similar theme to the last speaker. I don't think the need is I don't think we're at a stage where a single data set would be really useful. I think you really want to start figuring out what problem we're trying to solve. So that's identifying what use case is really critical. And I think a piece of that, I'd pick up on an earlier comment that Dave Meyer made. A lot of the places where machine learning is likely to be used is more of a, the output fits into some business workflow logic. It's not a traditional networking problem in that sense. So it's going to be very sensitive to business requirements, and it may not be static. So what's important to the business this week may be different to what's needed next week. So if you put those two together, what's probably more useful is a sort of life cycle view about how to handle these data sets, what characterizes a good data set, the sort of quality metrics that people talked about. That kind of approach is probably the most meaningful thing at this stage.
Okay.
Hi, Brent. Hi, Brian Trammell again. I just want to go back to very quickly to the point on data sequestration. This is a problem that we've had also in generally dealing with network data. And another venue that's dealing with this particular problem is MapRG. I don't think there's anything on their agenda about this meeting. They're meeting directly after this. But in general, sort of when you start talking about that or models for access to data, if that's a thing that you take up, definitely sort of crosstalk with that on the MapRG at IETF.org list would be, I think, useful for everyone involved.
Okay, so we have very good discussion.
Yeah, very well.
Yeah. So the next one.
Do you want to start a lady from Greece again?
Sorry?
The lady from Greece.
I don't have any news that the quality has improved.
Maybe we actually run short of time.
Yeah, we are short of time.
Yeah. Yeah. Since we had very good discussion in this meeting, so we used a lot of time, so we are much behind the agenda. However, I mean, this one could also take on the mailing list. So next page, please. This is what we originally have the motivation for this research group, the proposed research group. We want to have the network become more and more complicated. So we want many varieties and dynamically changing network to be able to match. Then machine learning was also one of the possibilities direction we can say to be able to handle those large and complicated situations in very short time. Because if we still rely on those if-else programming, so we may never to reach the target. Machine learning itself also motivated by tasks that are extremely difficult to program by hand. That's why we start this research group and provide a forum for researchers to explore the potential of mechanism, machine learning mechanism to network. We had running this for almost a year, if we count to the next meeting. For now, we already started a few use cases. So I guess we start to talking important to discuss what we may do in the future. Next page, please. I guess I jumped through this one. Yeah. Next page, please. Yeah. Actually, that's the last slides. We're already here talking about the possibility for standardized training data. It could evaluate the machine learning solutions. We know it's not for standardization, but in this research group, we could in the future agree a few data sets to be used to comparing each other for the solutions. And what we really want is not actually one of solutions. We don't, in the past, we saw a few machine learning mechanisms which may be designed for the network specific. We would like to, think about how the solutions or the designs could be generalized along the networks, at least a type of networks, not for a very specific single networks. So that's the one of the, I guess, could be the scope for in our future work. We are not going to contain the one-off solutions, but we would like to explore the what's the common between the network and what's the common solution we may have along network, which could benefit most of the network. Also, we see there are lots of different tasks in network area, thousands of them. Up to now, most of the use cases we say is task-oriented solution. So one of the questions we may want to work on in the future is whether there is common between those tasks, whether we can do some generalization along those tasks. I'm sure that's not possible to have the one goal for most of tasks, but whether it's possible, we build up some I don't know how to describe this. Maybe a machine learning infrastructure which has some common solution to analyze the network data, common data, and provide some primary results, which for specific tasks could take from there and to be able to get the result more quicker. Yeah. And if we could do so, that means we may be able to reduce the efforts for every specific tasks. And we say we would like to, this research group would like to get the guidance on how to apply machine learning in network area. So far, we are not sure how many guidance document we should have. That means first we need to agree on, or at least do some kind of gap analysis on, where we would do, where is the target audience, and where is the business requirements, what is the suitable use cases, and which gets the most concerned should be focused on. Next is the common characteristics of networks. As I said, one of the targets we want is to understand the foundation or the essential of networks by apply the machine learning mechanism. Again, it's still an open question. I'm not sure how we approach it without very specific task. But I mean, we maybe categorize our tasks into a few task groups. Then we may able to to try to use the machine learning mechanism on those categories, then to get some understanding of the network. Or another approach is we may start from the network categories to focus on different different networks and to find out what's common between along networks. Yeah, I already mentioned that. I'm not sure whether it's possible to build up a potential common network machine learning infrastructure or not. Do you want?
No, you can finish.
Okay. The next is we also touched that earlier is whether the machine learning could make the autonomic decision, create the closed control loop, or we just want to use the machine learning as the analysis tool for the human assistant only. I guess that will definitely, for now, will be case by case discussion, but I personally believe in the future we will all want to, move towards the autonomic design. One of the last thing is what we had in our original research group charter, but we haven't really discussed that at all, is whether we be able to unify the machine learning oriented information exchange protocols. So far, we don't have such protocol, but if we get a stage, we agree on certain common use of machine learning mechanism in common networks. So we definitely need some protocols to exchange the information or data connect from the network for machine learning purpose. Then we need such protocol, and we need to standardize their data structure. So that's something we could discuss in this research group. Definitely, if we reach that point, the standardization work will be in IETF, not in this research group. Am I right, Nas?
Yes.
Yeah. Yeah. Okay.
So I think one of the things I've not seen here for this working group as something that the working group could really do, or research group can really do and make an effect, is that you guys are located with IETF. I mean, who knows the internet better than IETF, right? So one thing that you could do is act as a conduit between the researchers at universities and the IETF in general, the service providers that run and the vendors that make this gear, and try to have some way on every IRTF meeting to invite the researchers to collaborate with the service providers. I mean, when I did my work in SIP-based machine learning, the number of papers that assume how SIP works and are way out of the ballpark, are tremendous. The thing that helped me is that I was part of SIP from the beginning, but this is the community that knows SIP inside out, right? And I believe that you guys are really sitting on a part where the universities ought to be incentivized to come and meet the service provider and the vendors, assuming they want to meet them as well. But that's where you can get something going. You talk about specific tasks. I think that should be one of the tasks. Leverage what the IETF has, and act as a bridge between engineering and research done here in corporations as well as in universities.
Yeah, good suggestion. Yeah, I mean, yeah, we're doing that, but most of people attend the IETF meetings no have access to the network data sets yet.
So Dave Meyer, I want to say something about the sequestering idea. Now, why don't we have this in sort of the ImageNet competition or in papers that are in NIPS or ICML? Why don't we have this? We don't have sequestered data. Why not? Well, I think the answer to this is that the machine learning community has a long tradition of openness, both open data, open source, and generally open science. in fact, if you want to publish a paper in one of the top 4 conferences, you know, ICML and EPSLS, you have to open source your code. They won't even look at your paper. So the gaming part of it, you know, that's not happening in our community right now. And I think that we should carry on that tradition of openness and don't allow people to show PowerPoint and no code. You know, show your code if you have a result, and show your data set so that somebody can replicate your result. That's a really powerful thing that's in the machine learning community right now, and it's always been there, sort of an open science kind of approach. And it kind of allows us to not have to deal with this idea of sequestration and things like that, right? So.
Fully agree. I actually, you know, definitely encourage that in the future, and maybe even in the future, sometimes we could consider to have the research group meeting, you know, set up with such whatever computation or whatever open source hackathon, something like that. Yeah,
I think so.
Yeah, but that will be something in the future and require very good organization, I guess.
Lee Howard, I'm going to respond to Dave first, because I don't think it's an either or. I think if we've got an algorithm, if you've got a hypothesis that you want to test and it works great against you know, cleaned up public data, then absolutely see if you can run it against a sequestered data set and see what kind of results you get, because that gets you much more robust results. And you know, obviously nobody's going to run an algorithm once and say, aha, we're done, right? That's not the goal.
I just want to say I totally disagree with the idea that that gets you more robust results. Openness gets you more robust results. And if you have a data set that I can't use, I can't look at with my algorithm, then I can't even compare it to what you did. So I would say it's the opposite. So.
Okay, well, so I'll sort of continue the theme there, because I work for a network operator and you're not getting my data. I might be willing to help you out by running your code against my data, but I can't legally release it. It's against the law. And I can't even, in many cases, I can't come up with a useful way to anonymize it. So
yeah, I guess the both you and David, you know, has the point, but the way we you know, get away from that is first we may working on the public open data, then
exactly what I was suggesting.
Yeah,
start it on public data, and just like the ImageNet example we were talking about, start it on public data, and it gradually you get cleaner and cleaner. You know, you get better and better algorithms, and if you eventually work on dirtier and dirtier data sets, that's a useful progression there. And but my goal isn't to publish papers. My goal is to have things working on my network.
And the algorithm need to be open source from the very beginning, and that in that case you can take that to apply in your network. So also the other providers.
Okay.
Yeah.
I have no objection to open source algorithms and code, but that's not a requirement for me as a network operator. I'm willing to pay money for useful things, right?
Yeah.
So, but I'm also back to, I didn't mean to laugh quite so hard when you said that we're co-located with the IETF, which, you know, who knows networks better, because network operators would laugh hysterically at that assertion. That's, you know, the network operator groups would say they know networks best. And actually, you know, you suggested co-locating a research group meeting with one of the conferences. You know, it would also be really interesting to co-locate with an operators group, because I think we're starting to get to the point where we've got some interesting questions that we want to ask. And I think that organizing some of this work along tasks that operators say, I have questions that you might be able to help me answer that I can't figure out the answers to. Those are fantastic research questions, and could actually then, you know, the soapbox I always get on is, you know, connect the research to, you know, to the actual deployment community, you know, operational community, and have the questions that we have come back to research and have the researchers provide useful answers. Boy, that would be fantastic. And I think, so I think that I'm sort of going back to make sure that I'm staying on topic, is I think that coming up with some specific tasks that we'd like to do analysis on, I think it's going to have to be iterative. We won't be able to do the generalizing until we've done the specific cases. Yeah. And I think that we won't be able to make general observations about general networks until we've, you know, tried a couple of different specific networks, and then see, you know, what can we observe from there. Mm-hmm. Thank you.
just
5 minutes.
yeah, just comes to the provider group. For the IETF research group, I don't think we have the tradition to have the meeting with provider group, but I don't think NAS will stop me for future meetings. Well, thanks.
Stephen, right. So two comments. One is in trying to set the scope here, I'm trying to understand where you would draw the dividing line between what's network related in terms of machine learning and what's not. What's really special about machine learning in the network context? And it's not so clear to me out of all of the presentations. I think there are a bunch of things that the IETF has, whether it's MIBs or Yang models that are very specific to things here that would be sort of data sources that you'd be learning from, but there's a ginormous amount of those, and correlating them with what's the output you're trying to get is a part of the problem that's missing. The second piece is I think you need to think about this in the context of virtualization as a trend that's going through the industry. So for one thing, your machine learning algorithm may well be packaged as a VNF and need to be delivered in that fashion. It may need to be attached to data sources. So how do you do that? Is one part of the life cycle piece.
I think that virtualization and SDN are really also relevant use cases.
But I think it also gets to the way you draw the dividing line, because if you think of it in that context, then you have a bunch of data sources that aren't necessarily IETF centric. So if you're running in a virtualized system on OpenStack and Daylight or something like this, you've got a bunch of other data variables that may well be very interesting if you're trying to do fault correlation, for example. So it gets back to where do you draw the line? It's
Yeah, so your laugh was actually interesting to me, and I started thinking, why did you laugh? And then it struck me that what I was trying to say was not that the IETF has lots of experience in running networks, but we have tons of experience in designing protocols and knowing exactly why this bit is the way it is and when did it come about. And that's the thing that could be leveraged. You have lots of SIP experts here. You have lots of researchers that are doing work on SIP, for instance, and running machine learning. So connect those folks together. And I was using IETF more as a larger organization rather than, but that's the point I was trying to make.
Yeah, thanks. Any more? Yeah, Brian?
Brian Carpenter. I'm just struck that that's a very ambitious program. If you follow all those future directions, you need 1, 2, 3, 4, 5, 6 research groups. So I think you have to be cautious about launching too many things in parallel. In terms of final goals of producing output ideas that can actually be used by the IETF, I'm most interested in the first bullet and the last one, which is about how you do information exchange, because you can't start designing machine learning algorithms and how they work internally here, but you can certainly think about how information should be exchanged between the components in a complete system.
Yeah. First, the answer to what Brian said, there are too many. Actually, I don't think, for now, we can really work on the generalization. We have to work on specific use case first. So the bullet second is out, and we definitely want to work on some gap analysis first. Then, if so, we may give out some kind of guidance. So the third point, stay on, and the fourth and also the fifth. Fourth and fifth is still in future work for long-term future. So for now, we actually only probably take 1, 3, 6. So 3 of them. No?
Yeah, last second, I just want to basically remind people, so the process for starting new work in the IETF is pretty undefined, and what I've been using as IETF chair is basically I tell people like, Jane, that comes with an idea, I'll give you a year, I'll give you a few meetings, have the meetings you want to have, run as if you are a group and do that, right? And that's been happening here for a couple of meetings now. I missed one of those because I was on parental leave, right? So you met 3 times now, but I wasn't there. So it's, I'm not going to make any decision right after this meeting. I think we're going to let you continue running until maybe Seoul or something like that. I will make a decision before I step down, which is next March, because I think it's sort of my duty to decide on the future of the NMLRG and the MapRG. Those are the 2 proposed groups we have at the moment before I hand it off to my successor, because it's really unfair to basically drop something on them that they had no, say in how it's going to run. So we will decide for both of these groups before I step down. I'd be very interested in hearing from people what you think as participants about how this group is going. This is, I think, the first. I've been to the very first meeting, and then I've been to this meeting, and I'm sort of torn, right? Because I see there's a lot of interesting potential here, right? Where you have operators interested that want to have questions answered. I also think there's still a lot of confusion here, and this list to me actually, I really liked on your previous slide, the very bottom bullet that you had that said, it's a forum where researchers can talk to vendors and operators and customers in order to, no, that was actually not the one, maybe it was that one. So I like that last bullet because that I can understand what kind of group this is. This long shopping list of future direction to me looks very confused because it means we could do everything, right? And yes, we could, but if you pick some things, right? So there's 2 ways in which you can do this. You can pick some things specific, short-term, more focused, but that means you're excluding a bunch of other stuff that's maybe relevant, and especially things that come from research. And this is kind of a hot area, so things are popping up, and you can't really know what's going to be, coming out. Excluding things because you're focusing down excludes people, which is probably not what we want to do in the beginning of a group. So this getting researchers in here to talk to more practically oriented network people and figuring out what the overlap is and what are some specific things that can be done is maybe a way forward. I'm neither a network machine learning person. I'm not a machine learning person, and I'm barely a networking person. So leave that as may. But sort of the future is basically going to be, we'll see how this goes. I'm very interested in hearing, in the coffee break from people, if you want to come and talk to me or send me email, how you think this is going, right? If you were me, would you charter this, or would you say, it didn't come together? Which is a fine answer, right? The groups don't come together not because the technology is bad or the organizers didn't try hard enough, or there's many reasons why things don't work. So I'd be very happy to hear about this. Right. Thank you.
Thank you. We are perfect in time.
Yeah,
2 minutes late. Just before you go, make sure you sign the blue sheet.
Thank you.